Hello and welcome back to another fascinating exploration. Today, we're diving deeper into the revolutionary perspectives Dr. Alok Aggarwal shares in his book, The Fourth Industrial Revolution and 100 Years of AI.
So last time we really dug into the nitty-gritty, huh?
Yeah,
We talked about keeping those AI systems running smoothly. It was all about maintaining the data pipelines and updating the models, and that whole complex world of AI governance. It's a lot to wrap your head around.
it is.
But today we're going even deeper, zooming out to consider the very foundation of computing itself. Moore's Law. What happens if it hits a wall?
That's the big question, isn't it? And that's what we're diving into today. But we're taking it even further. We're also venturing into the mind-bending world of quantum computing. We'll look at how it could revolutionize our current computing infrastructure and uncover its most promising applications.
Moore's Law has been this incredible driver of progress, like for decades, right?
Yeah,
And it's led to this exponential growth of computing power,
it has. But what happens when we reach the physical limits?
right?
When we can't physically cram any more transistors onto a chip?
I mean, we're talking about the very limits of physics and engineering.
We are.
It's wild. And speaking of wild, the book mentions that transistors are already just a few atoms wide. That's just insane to me.
It's incredible.
It's like science fiction.
It is astounding. To give you an idea of just how small we're talking, a 5-nanometer transistor, which is what's in many of our devices right now, is about the width of like 5 silicon atoms.
Wow.
And the cost of building a manufacturing plant for these tiny components? Over $500 million.
No way.
We're talking about monumental engineering feats here.
Absolutely.
But it's not just about the cost.
Right?
The real problem is that at these sizes, we start running into the fundamental laws of physics,
Okay, so it's not just a matter of money or engineering prowess at this point.
right?
The universe itself is setting boundaries.
It is.
I'm intrigued. Tell me more about these limitations.
Imagine trying to control the flow of electrons, which is essentially what computation is all about.
Gotcha.
At the macroscopic level, it's fairly straightforward.
Right?
But when you shrink down to the atomic level, things get really weird. Quantum effects start to dominate.
Quantum effects.
Yeah, you have things like quantum tunneling, where electrons can basically teleport through the barriers that they classically shouldn't be able to cross.
Seriously.
Seriously. It's like trying to direct traffic when the cars can suddenly disappear and reappear at random.
So it's not just that transistors are getting harder to build, it's that they're becoming less reliable at these sizes
Exactly.
because of these quantum shenanigans.
Yes. And then there's Heisenberg's uncertainty principle.
Ooh, Heisenberg. Now we're talking. So remind me, what is Heisenberg's uncertainty principle again?
It's a fundamental concept in quantum mechanics that says we can't know both the position and momentum of a particle with perfect accuracy.
Right.
The more precisely we try to measure one, the fuzzier the other becomes.
So how does this actually limit computing speed?
Well, think about it. If you can't precisely pinpoint where an electron is, you can't control its movement with perfect accuracy.
Makes sense.
And that movement of electrons is what drives computation.
Got it. So Heisenberg throws a wrench in the works,
He does. And then you have the speed of light.
right? The ultimate speed limit.
Exactly. These factors combined essentially set a ceiling on how fast information can be processed.
So the combination of factors,
Yes,
the weirdness of quantum mechanics at tiny scales, the fundamental limits imposed by Heisenberg's principle, and the speed of light itself, we're hitting a wall,
we are. And it's not just about the CPU either.
right? It affects everything, right?
It does. Memory, internal clocks, power consumption.
The whole shebang.
The entire electronics industry is facing this fundamental challenge.
So the big question is, what happens next?
What happens next? Good question,
If Moore's Law is ending, where do we go from here?
right?
What does the future of computing look like?
It's exciting to think about.
It is. I know there's been a lot of buzz about quantum computing. Is that the answer?
Quantum computing is a very fascinating prospect,
It's always kind of framed as this next massive leap forward in computing.
right?
What does that even mean?
Yeah. Well, the push for quantum computing comes from a problem that we're hitting in our current technology. And it's the fact that we're hitting the limits of Moore's Law,
Yeah, like we're getting down to the atomic level.
right? Exactly.
We can't keep shrinking things forever, right?
We can't. And we're kind of reaching a point where the laws of physics are starting to say, no, you can't do that anymore. And that's where quantum computing comes in. It's not just a faster computer. It's a fundamentally different way of processing information.
Okay, I'm intrigued.
Yeah,
So what makes quantum computing so different from the computers we use every day?
it leverages the strange world of quantum mechanics. So think of it like this. In the computers you're used to, information is stored in bits, which can be either a 0 or a 1.
Right?
But in quantum computing, we use qubits.
Qubits?
Qubits, yeah.
How are they different?
A bit is like a coin. It can land on its head or tail. It's definitely one or the other.
Yeah.
A qubit, though, can be heads, tails, or both at the same time. It's called superposition, and it's one of the mind-bending principles of quantum mechanics.
So a qubit can be two things at once.
Yeah, it's a little bit like if that coin was spinning in the air before it lands. Until you stop it and look, it's potentially both heads and tails.
Right?
That's the power of superposition. A single qubit can hold vastly more information than a single bit.
So if one qubit can be in two states at once, what happens when you have multiple qubits?
Then things get really, really interesting.
Okay.
So 10 qubits in superposition can represent over 1,000 possibilities simultaneously. 20 qubits, over 1,000,000. 30 qubits, you're talking about over 1 billion possibilities.
It's like having millions of computers working on a problem at the same time.
Yeah.
All within one machine. That's incredible. So what's the catch? There's got to be a downside, right?
There are a few, actually. One of the biggest ones is that quantum computers are notoriously difficult to program. The way they process information is so different from our everyday experience that even experts have a really, really hard time wrapping their heads around it.
So it's not like learning a new programming language.
No.
A whole new way of thinking.
It's a whole new way of thinking. Yeah.
Oh, okay.
And then there's the issue of extracting meaningful results.
Okay.
So you remember how a qubit can be in multiple states at once? Well, when you measure a qubit, it collapses out of that superposition and it becomes a definite 0 or 1.
So all that computing power just vanishes when you try to get an answer out of it.
Yeah, that's one way to think about it. Think of it like trying to capture a really rare bird.
Okay.
Like the act of observing, it changes its behavior. So figuring out how to harness the power of all those calculations before measurement collapses them back into a single result, that's the challenge.
So we've got this incredible potential for parallel processing, but getting usable result, it's like trying to catch lightning in a bottle.
Yeah.
Okay, so we've got programming is incredibly difficult. What else makes quantum computing tricky?
Well, there's this concept called entanglement. So imagine you have two of those spinning coins, and they're linked in a way that if one lands on heads, the other instantly becomes tails, even if they're miles apart. That's the basic idea behind entanglement.
That's wild. So it's like there's this hidden information shared between these qubits.
Exactly. Entanglement adds another layer of complexity and potential to quantum computing, but it also makes programming and controlling these systems incredibly difficult, because you're essentially dealing with a web of interconnected information.
So it sounds like even something simple like sorting numbers wouldn't be so straightforward with a quantum computer.
You're right. And while there are quantum algorithms that can sort numbers, we haven't figured out how to make them drastically faster than what we can do with traditional computers.
So it's not just a matter of plugging in any problem and getting an instant answer.
No, not at all. Even the breakthroughs we have, like Grover's algorithm for searching data, they are incredibly complex and rely on really deep principles of quantum physics. And essentially what this algorithm does is it cleverly exploits superposition to search through massive data sets much faster than any classical algorithm can.
So even the things that we have achieved with quantum computing are pushing the boundaries of what we know about physics.
Absolutely. And that's just one example. Imagine the potential if we could harness the power of quantum computing for even more complex problems.
This is getting interesting. Okay, so we've got these incredibly powerful systems. They're difficult to program. And getting meaningful results is a challenge.
Yes.
What other disadvantages are there?
One major factor is data size. Right now, the speed advantages of quantum algorithms are really only noticeable when you're dealing with massive data sets. Think trillions of words or more. Anything smaller, a classical computer can often do the job just as well, if not better.
So it's not like these are going to replace our laptops anytime soon.
Right?
Are there any other security concerns besides what we've already discussed?
Actually, yes, because quantum computing relies on these strange principles of entanglement and superposition. There's concern that somebody with a deep understanding of these principles could exploit them for malicious purposes.
So someone could theoretically hack into systems that are currently considered super secure.
Exactly.
Wow.
It's a potential risk, especially for organizations like governments that rely on highly secure systems. It's just a reminder that with any powerful technology, there's potential for misuse.
That's a sobering thought.
Yeah,
Okay, so we've talked about all these disadvantages. What about the process of actually building and using these quantum computers? It doesn't sound like it's anywhere near commercially viable yet.
no, you're right to be skeptical. There are some major hurdles to overcome before quantum computing becomes mainstream. One of the biggest is that the qubits themselves are incredibly fragile and prone to errors.
So building a quantum computer isn't as simple as just connecting a bunch of transistors.
Not even close. Maintaining a stable quantum computer is a huge engineering challenge. And then there's the issue of scaling up.
Okay, I'm guessing that means building quantum computers with more qubits.
Exactly. Right now, the most advanced quantum computers have around 1,000 qubits. But to be truly cost-effective and tackle the really big problems, we're probably going to need systems with 1,000,000 qubits or more.
1,000,000 qubits? That sounds incredibly difficult and expensive.
It is, and we're not even talking about the extreme conditions these things need to operate in.
What do you mean?
Most quantum computers require temperatures near absolute zero,
Wow.
which is negative 273 degrees Celsius, and they use incredibly expensive materials.
You're telling me these quantum computers need to be kept colder than outer space.
That's right.
Wow.
It's not exactly something you can plug into your wall socket at home. There are some startups like Quantum Brilliance that are trying to build quantum computers that can operate at higher temperatures, but commercial viability is still a long way off.
So it seems like quantum computing is this incredible technology.
Yeah,
Mind-blowing potential, but there are also some major challenges it should overcome.
definitely.
Where do you think we'd go from here?
That's a great question, and it's one that researchers and scientists are working hard to answer. Despite the challenges, there's this sense of excitement and possibility surrounding this field.
Yeah.
And while we've been talking about some of the limitations of quantum computing, it's important to remember the incredible advantages that these systems offer.
Yeah, you're right. It's easy to get caught up in the challenges. Let's get back to that mind-blowing potential for a minute.
For sure.
We talked about how quantum computers can work on all those possibilities simultaneously, thanks to superposition. What kind of real-world problems could that kind of power help us solve?
So imagine problems that are impossible for even the most powerful supercomputers today. Things like simulating complex molecules for drug discovery or optimizing global-scale logistics.
Okay,
These are the kinds of challenges where quantum computing could be a game changer.
can you give me a specific example of how that might work?
Absolutely. So let's take drug discovery. Right now, developing new medications is a really, really long and expensive process.
Yeah,
Scientists have to test out literally thousands of potential compounds to see if they work. But a quantum computer could simulate the interactions between molecules at an atomic level, allowing us to identify the most promising candidates much, much faster.
so instead of running like physical experiments, you could run millions of virtual experiments in parallel.
At the same time,
That would revolutionize medicine.
yes, and it's not just limited to medicine. Quantum computing could impact fields like materials, science, finance, artificial intelligence, and even cryptography.
Wow. That's a pretty wide range of applications, but you've also highlighted some serious challenges.
Right?
So where do things stand right now in terms of actually making quantum computing a reality?
Yeah, so it's still early days, but progress is being made. We're seeing significant investments from both governments and private companies. Researchers are constantly making breakthroughs in areas like qubit stability and error correction.
It sounds a bit like the early days of computers, right? There were these massive, expensive machines that only a handful of people could use.
That's a great comparison. And look at us now. We all carry around smartphones that are more powerful than those early computers.
Right. It's hard to predict exactly when quantum computing will become widely available and affordable, right? But I'm confident that it eventually will happen.
Oh yes, imagine if you could just snap your fingers and your computer could solve a problem that would normally take years.
Like magic.
There's definitely a ton of potential. But it's important to remember that quantum computing is still very much in its early stages. One of the main reasons it hasn't completely revolutionized everything yet is the complexity of the underlying quantum computation model. It's a whole new way of thinking about computation.
So maybe no snapping fingers just yet.
Not quite.
But something that really caught my eye was this idea of quantum computers being able to break cryptographic algorithms.
Right?
That sounds a little unnerving, to be honest. What are the real-world implications of something like that?
Well, think about it this way. A lot of our online security right now relies on the fact that it's really hard for regular computers to factor in really big numbers. That difficulty is what keeps things like online banking and email secure. But back in 1994, Peter Shor came up with this quantum algorithm that can factor these huge numbers much, much faster.
Wow.
And this means that, in theory, quantum computers could crack the codes that protect a lot of our digital lives.
So it's not just a hypothetical problem. It could actually make the internet a much less secure place.
Exactly. And that's just one example. There's another algorithm, Grover's algorithm, that can search through trillions of data points, billions of times faster than a classical computer.
I can't even wrap my head around that.
It's hard to grasp.
Searching through that much data a billion times faster. What does that even look like in practice?
Okay, imagine trying to find a specific needle in a haystack the size of a major city. That's what searching through that much data is like with a traditional computer.
Oh, wow.
Now, shrink that haystack down to the size of a small room. That's the kind of speed up we're talking about with Grover's algorithm.
So it's not just about finding specific pieces of information. This could speed up any kind of search.
Exactly. Grover's algorithm works on unstructured searches, meaning it can be applied to pretty much any kind of data you can think of.
That's wild. The book also mentions an algorithm from 2008 that can solve linear equations exponentially faster.
Yeah.
Remember from math class that those equations are everywhere. Science, engineering, even AI.
You're right. And this is where things get really interesting. This algorithm could potentially speed up existing algorithms, even ones like Shor's and Grover's.
Really?
It could also totally change how we do machine learning and allow us to run much more complex simulations than we ever could before. Imagine what that could do for something like weather forecasting or developing new materials.
Okay, so we've got these incredible potential speed-ups, but is there a catch? Is this all just theoretical, or are we actually seeing these results in the real world?
That's the big question, isn't it? The theory is amazing, but putting it into practice is really challenging. Like, take Google's Sycamore processor, for example. In 2019, it made a huge splash because it solved a problem in 200 seconds that would have taken a classical supercomputer 10,000 years. It seemed like proof that quantum computers were vastly superior.
So that was a big win for the field.
It was, but there's more to the story. Researchers in China later developed a classical algorithm that could solve the same problem in just 15 hours on a much less powerful computer. It was a good reminder that the field is constantly changing, and what looks like a quantum advantage today might be matched by classical computing tomorrow.
So this debate about quantum supremacy is still going on.
Exactly. It's good to be excited about the potential, but also important to be realistic about the challenges.
Speaking of reality, what's the current state of quantum computing? Are there actual quantum computers out there that people are using?
There are, and they're getting more powerful all the time. IBM, for example, has been making big strides. They've launched something called the IBM Q Experience, which is a cloud-based platform where developers can try out quantum software. They also developed the 127-qubit Eagle processor, which is one of the most powerful quantum processors available right now.
So it sounds like things are moving pretty quickly, but we're not quite there yet. When do you think we can expect to see quantum computing become more mainstream?
Well, experts think it could be at least another 15 years before quantum computing really becomes mainstream.
Okay, so 15 years down the road. Now I'm curious, while we wait for quantum computers to really take off, are there any other technologies on the horizon that could help us overcome the limitations of traditional computing?
There are, and that's what makes this whole field so fascinating. There's a lot of really cool stuff being worked on right now.
Okay. Let's take a second to recap what we've learned so far. We've talked about how Moore's law, which has driven this massive growth in computing power for decades, might be hitting its limits. And we've seen how quantum computing is emerging as this potentially powerful alternative with a whole bunch of possible applications.
From cryptography to drug discovery, the potential is huge.
It really is. And for those of you who are curious about what else is out there, in the next deep dive, we'll be exploring 4 other alternatives to traditional computing and storage.
We'll also look at the rise of these specialized processors that are used to train AI algorithms, and the increasing use of specialized processors for making predictions and decisions once those AI models have been trained.
It's going to be another exciting exploration.
We can't wait to have you back. So until then, keep exploring, keep learning, and stay tuned.